Neural ODE is a recent machine learning model that has gained prominence in time series modeling over traditional neural networks. And since Neural ODE is recent, few verification tools are compatible to it, and the current available tools are computationally intensive. In this paper, we leverage TIRA tool based on mixed monotonicity for Neural ODE, using two continuous time mixed monotonicity methods with 3 approaches, and we compare the performance of our methods with other Neural ODE reachability analysis tools. We consider the following Neural ODE, and we define the Neural ODE reachability for a given initial input set, and the green phi is the solution to the state trajectories of equation 1 based on the corresponding initial value problem. The homeomorphism property preserves the topological characteristics between two continuous sets, and assuming that the two sets x and y are closed and bounded, then the mapping function maps boundaries to boundaries and interiors to interiors. And since Neural ODE were proved to be naturally invertible, then they are homeomorphic. The Neural ODE is considered to be mixed monotone if there exists a decomposition function, and this function is increasing in the first argument and decreasing in the second argument, and the vector field f is embedded in its diagonal. The only required condition for applying continuous time mixed monotonicity is to bound the Jacobian matrix of the Neural ODE. And this corresponds to the blue part here, where we first compute the reachable tube over approximation of the system using any available Neural ODE reachability analysis tool, and then we compute the Jacobian bounds using interval arithmetics. For our numerical examples, we reuse two commonly used academic examples, which are a 2-dimensional spiral system and a 5-dimensional fixed point attractor system. Here we are proposing 3 Neural ODE reachability analysis approaches, where for the single-step approach, we compute the reachable set over approximation directly from the initial time to the final time, while for the incremental approach, we divide the time horizon into smaller steps, computing intermediate reachable set over approximations. And finally, for the boundary approach, we take advantage of the homeomorphism property of Neural ODE to compute the reachability over boundaries only. So for the spiral 2D system, we are computing only over 4 boundaries, resulting in the blue zonotope here. And similarly, for the FPA system, we will compute over 10 boundaries as the FPA is 5-dimensional. This approach offers computational efficiency for both low and high dimensional systems, as it scales linearly with the state dimension. For the spiral system results, some of the resulting TIRA over approximations were identical. However, the incremental and boundary-based approaches require more computational time than the single-step approach. In terms of over-approximation tightness, both CORA and NNV achieve tighter over-approximations than TIRA. However, TIRA achieved the fastest computational time for the single-step method than CORA and NNV. Similarly, for the 5-dimensional FPA system, some of the resulting TIRA over approximations were identical, and in terms of over approximation tightness, CORA achieved tighter over approximations than TIRA, and here as well, TIRA achieved the fastest computational time over CORA and NNV. So to conclude, we have proposed a novel lightweight interval-based Neural ODE reachability analysis method, and this approach is based on continuous time mixed monotonicity, and the numerical experiments demonstrated that our methods produce sound over approximations, which are faster in terms of computation than other more flexible set representations.